Hello mates, as you can see we have just finished our circular motion. If you are following this as a series, we have finished our circular motion. Now we're getting into gravitation. So let's get into that part. Let me take this paper. Okay. So our third topic is going to be gravitation. To start off gravitation, we are going to just state three laws that I think for me I would say that took off this field of study. We're going to state Kepler's laws, and I'm going to be using diagrams to and just saying out what they say. The first law says planets describe ellipses about the sun as one focus. So the planets, they have the orbits that are elliptical like this. Let's say this is the Earth. And you know, an ellipse has two foci. I think there's going to be a focus point here and another focus point there. So they're saying, the first law says the sun has to be at one of the focus, at one of the focus points. So that's the first law. The first law says the planets describe ellipses about the sun as one focus. So it will be like this, and then the Earth, this focus point is not necessary there in what? In that explanation. So the Earth revolves around the sun in these what? Elliptical orbits. And then two, the second one says the line joining the sun and the planet sweeps out equal areas in equal times. This basically means something like this. The sun will be here. So this is the sun, and then this will be our lovely Earth. So they're saying the line joining the sun and the planet Earth. So let me rather not put it there. Let me rather not put Earth here. The second one, let's say the Earth is at this point at time t1. Then the line joining the sun to the Earth will be like that, right? And then at time t2, let the Earth be there, t2. So the sun, the Earth will be, the line joining will be like this. So the second point is, imagine this time period is equal to t. For it to move from this point to that point, imagine it's equal to t, which may be 30 days, 2 days, or whatever. But this law is saying in equal times, this line joining the sun and the Earth sweeps out equal areas. So imagine now I start at this point. If I start at this point as my t1, in equal times, if it's going to be period equal to 30 days, so if I start there in 30 days from this point, it will be maybe at this point here, t2. After those 30 days, this line joining the planet and the sun will sweep out equal areas in that 30 days. So when it's on this side, it sweeps out this area, and when it's on that side, it sweeps out this area. They are basically saying this area A is equal to area B. That's what they're basically saying, because here it takes what? 30 days as well. So if you're considering equal periods, 30 days to sweep out a certain area, maybe on this side, considering that on this side the same day, the number of days, it will sweep out an area maybe different in shape, but the area will be the same. So that is the second law, Kepler's second law. And then Kepler's third law says the squares of the periods, t squared is directly proportional to the cube of the what? Of the radius. So this basically means stating it properly, it says the squares of the periods of revolution of a planet, of planets, are proportional to the what? To the cubes of their mean distances from the sun. So let's say there's the sun here, and there's planet number 1, planet number 2, planet number 3. These will be the distances from what? From the sun. So the periods of these planets are directly proportional. The period squared of these planets are directly proportional to the cube of their radii from the what? From the sun. So which means this one here, since it is r, the r cubed, it will have a longer period than this one here. Using what? Using this third law, which says the squares of the periods of revolution of planets are proportional to the cubes of their mean distances from the sun. So that is at Kepler's law number 3. So now let's get into Newton. Newton knew about this because Kepler came before Newton. He knew about this, and he started building his universal law of gravitation around this, trying to make his law consistent with these 3 laws. So let's get into Newton's law of gravitation. Newton's law of gravitation. Along came Newton, and Newton made some assumptions. The first assumption is one we are going to make. We are going to assume orbits are circular. You know, from Kepler's first law, he said that orbits are elliptical, but for simplicity's sake, I don't know how that was, a tongue twister, but for simplicity's sake, we are going to assume that the orbits are circular. This is what we are going to assume. So now, when we are considering circular orbits, it now makes sense why we had to do circular motion before, because now Newton considered motion of a planet around the sun in a circular orbit, right? So let's draw the planet. So let this be the circular orbit, and let this be the sun, and let this be what? Be planet with a mass m. That will be planet with a mass m, and it's what? It's revolving in a circular orbit around the sun. There's going to be gravitation that is pulling it, which is the what? Which is the centripetal force. Is going to be gravity due to the sun. So force, we know that the force is going to be the centripetal force, because this planet is the force on this planet. Actually, the force on this planet is a centripetal force, because this planet is moving in a circular orbit. How did we use to calculate centripetal force in the circular motion section? We used a formula. We used F is equal to what? To mRW squared. If you remember, that was one of the formula for calculating centripetal force. F is equal to mRW squared. But we know, W is equal to 2 pi over T. Therefore, this force of gravity is equal to mR 2 pi over T squared, which is equal to 4 pi squared mR over T squared. This is just playing around with formula, but as long as you know this and you know this, then you're fine. I'm just now playing around with the formula to come up with this one here. So this is the force of attraction of the sun on the planet. So it's the force of attraction of the sun on the planet. I could write it like this: of F of S on M. F of S on that planet M. So now that's what Newton discovered. Newton assumed circular orbits, isn't it? We are now deducing Newton's law of gravitation. Newton assumed what? Circular orbits. Then he was like, okay, if it's a circular orbit, there's going to be a centripetal force. And I know that centripetal force from circular motion is calculated like this. But I also know that from circular motion, W is equal to 2 pi over T. So this force here is given by this. That's what he knew at that time. So this force is given by that. So now he then, with this genius, because Newton was a genius, he was out of this world. Newton was just a genius. He then later on went to assume an inverse square law. He assumed that this force here decreases as the radius increases, but it decreases observing an inverse square law. An inverse square law basically says one quantity here will decrease, will be inversely proportional to what? To the square of another quantity. So that's what he assumed. He assumed that this force is inversely proportional to the radius, but the radius squared. That's the inverse square law. So his assumption was this force Sm is inversely proportional to 1 over r squared. As the radius is increasing, the force will decrease, but it won't just decrease proportionally. No, it will decrease with the square of the radius. That's what he assumed. Therefore, from his assumption, our Fsm is equal to k over r squared, just to put k as the constant of proportionality. So this is his assumption that he used. And then after that, you also notice that force. You also notice the force force of gravity on any object also is directly proportional to the mass of that object. If the object is small, the force of gravity will be small. But if the object is large, if it's large, the force of gravity will be large. So it made sense for him to use this proportionality to say this force FSM is directly proportional to m. It made sense for him to make this assumption as well. So he injected that into his assumption. FSM is equal to k over r squared. Therefore, his overall assumption was the force on a planet m is equal to k, the constant of proportionality, m over r squared. This was his assumption. So he then what? He then equated the two. The one from centripetal force that he had calculated, this one, and his assumption, this one. So here he assumed that this is equal to r over t squared, as we have seen from what? From just considering circular motion, not even considering gravity or anything, just considering circular motion, he came up with this. Consider circular motion, he came up with this, and we also did come up with the same conclusion. And then from his genius assumption, he came up with this. So he equated the two quantities. When he equated the two quantities, it was km over r is equal to that. So now he then tried to calculate the period. So making t the subject of the formula, t squared will be equal to, multiply both sides by t and multiply both sides by r. So this one will be 4 pi squared m r cubed, because this r is going to go that side, and divide by km, all divided by km. This m will cancel this m, and this k is just a constant. So t squared is equal to 4. I'm going to write it this way so you see where I'm going with this. 4 pi squared over k r cubed over like this. But can you see this part here? This part here is just a constant. It's a constant. So we can take it, because 4 is known, pi is known, k is already a constant. So we can take this as just one constant. And we can then take it out. When you take it out, it basically means t squared is directly proportional to r squared. Therefore, t squared is directly proportional to r cubed, like this. T squared, I made a mistake actually when I said it before. So t squared is directly proportional to r cubed. Then he reached this conclusion by taking out this. When he reached this conclusion, I imagine how happy he was, because it was consistent with the guy who had said it before. Kepler's third law of motion had said t squared is directly proportional to r cubed, which then meant that his inverse square law assumption was on the right track. It meant that this assumption that he had made was on the right track, that the force on a body, force of gravity on a body, decreases as the square of the radius, and is proportional to the mass of the object being what? Being in question. So he was happy that his force can be calculated using this. It was now a matter of just getting what this k is, because if he had found this k, then he would have found a universal law. Now he went on to do many experiments testing out the inverse square law to the moon's motion, which has a period of t is equal to 27.3 days. He then did many experiments trying to figure out what that k was. So now he knew that he knew the period. He knew the period of the what? Of the moon, and he also used f is equal to m, the radius of the moon squared. So he was considering a situation like this being the earth and this being the moon. That's the situation he was considering, this being the earth and this being the moon. So in this situation that he was considering, this radius was the radius of orbit of the moon. These were known quantities in his day. They were known quantities in his day. So here he just put f is equal to mr 2 pi over t, just like we did before. This is equal to 4 pi squared mr over t squared, isn't it? if the planet was at the Earth's surface, then he started making assumptions. So I think in the next video, because the 15-minute mark is almost up, in the next video we are going to continue his deduction.